Welcome to Mr. Sweeney's AP Physics C, Dynamics Notes number 5 on drag force. And drag force occurs when a body moves through a fluid such as air, can be water or some sort of oil or other liquid or gas. When the body moves through this fluid, it experiences a drag force that acts on it opposite the direction of its motion. So whatever way it's going, drag force is always pointing opposite. Drag force is very similar to force of friction there. They're both retarding forces or resisting forces. They both act as dampening forces, so that way something moving through them or the motion of an object is always pushed and resisted. And we see drag forces as well as frictional forces all over in our environment. Symbolically, we represent drag force with the force symbol with the subscript D. You will also see drag force represented as the capital letter D, and these can be used interchangeably. When you look at drag force, the main factor in determining the drag force, or at least the variability within drag force between the system, is the velocity of the body through the fluid. There's many factors that do impact drag force, like texture and cross-surface area, the density of fluid. So there's lots of factors that affect it in and of itself. But as the object moves through, velocity is the factor that is variable with the drag force. Now for drag force, we do have this equation, and this says that drag force equals 1/2 times the coefficient of friction times the density of the fluid it's moving through multiplied by the cross-sectional area of the body that's moving through the fluid multiplied by velocity squared. This is the technical definition of it. There are many approximations. We will not be using this equation in our class. We will be using approximations, but this equation does capture how drag force is calculated. Terminal velocity. Terminal velocity occurs when the drag force acting on an object is equal to the net force of all the other forces acting on the object. So all the forces acting on the object would give this object some net force pushing it in a direction. Eventually, the drag force will become so much that it equals all these other forces, in which case there's no net force on the object no longer accelerates, and at that juncture the acceleration is constant. We refer to this constant acceleration, or this constant velocity, as terminal velocity. And for falling bodies, because we can consider terminal velocity on any type of object that has a resisting force, typically the most common application of this is for falling bodies. In this scenario, when the force of gravity acting on the object is equal to the drag force, you've hit terminal velocity, you are going as fast as you will be going. Earlier, when we had introduced the drag force equation, I had mentioned that approximations of this drag force are typically used in this class. And we use two different approximations. The first a little more often than the second, and this is at a low speed. So if you have an object that's moving at low speed, the drag force is linearly proportional to the velocity and can be approximated with this equation. Drag force equals some coefficient times velocity. You see this used a lot for like cars or things on the ground. Oftentimes drag force there is a very close approximation to velocity linearly. Oftentimes you might even see frictional forces or a generic frictional force represented by this. And this could be friction equals negative kV. It's a very common, say, automobile problem where they might consider, as the velocity goes up for the car, the ability for the engine to continue to have the output that it has decreases. You also have an increasing amount of air resistance. So they might ball all those different types of velocities all together as one coefficient k, or b, or any coefficient number for that matter. When you get to high speeds, there's a little bit more sophisticated situation here, because now, instead of it cutting through the wind, objects that are moving at a high speed cause turbulence, primarily as being the new factor. And this turbulence causes the velocity to have a little bit of a different type of reaction when it comes, or different relationship to the drag force. In this scenario, we still look at the same general idea where we're taking all our coefficients and all our values and we're collectively representing them by one coefficient. But now we're looking at the velocity squared. This most closely resembles the approximation of the actual drag formula. So anything that's going at a high speed, we'll typically find that it's a squared relationship to the drag force. At the slow speed, it would be everything can be combined as one coefficient times velocity. If it's high speed, everything's combined as one coefficient, and then you have the velocity squared. That wraps it up for this video. We do have a lab coming up on drag forces that we'll be looking at next week.